Hey Dr. Wu, my name is Arunkumar and I am presenting my project entitled Hand Position Based Wheelchair Interface for the Physically Challenged. Moving into the project, so this is the introductory part of my presentation. At the end of my presentation, I will be giving a short demo of my code in action. My project aims to make the lives of patients who are suffering from paralysis easier. There are a number of different types of paralysis that could affect a person. They are generally classified into paraplegia and quadriplegia. Paraplegia is where the ability to move your legs is compromised while your arms are fully functional, while quadriplegia means all limbs are paralyzed. Sufferers generally end up being wheelchair-ridden or bedridden. They are unable to move their limbs to any significant extent. Paralysis can be caused by genetic characteristics and injuries such as a broken neck or infection that could affect the nervous system. Depending on the extent of paralysis, patients may have extreme difficulty in interacting with the world, even to the extent that they may not be able to operate wheelchairs. So many of these patients are actually confined to wheelchairs, and there are many different classes of wheelchairs that address their differing needs. The most basic type is the manually powered wheelchair, where the patient has to provide the effort needed to move the wheels on the ground. This is typically not applicable to patients of paralysis. Motorized wheelchairs are the norm, and they could be controlled by joysticks or keypads. Even though they are said to be the most inexpensive type of wheelchairs other than the manually powered ones, they could still easily cost in excess of $2,000, and a lot of patients, particularly in third world countries, may not be able to afford them. In the case that they are not able to afford them, these patients may have to spend their time in bed or be dependent on a nurse. The operation of such wheelchairs depends on the ability of the patient to exert force to move the joystick or press the buttons on the keypad, and many patients may not actually have this faculty. Here is a image of a typical motorized joystick based wheelchair. So you can see the joystick control on the right palm rest of the wheelchair. So I'll just highlight it here. As you can see, this is where the patient's hand rests, and he is expected to move the joystick with his fingers so that the wheelchair may be steered. There are also other types of wheelchairs for more advanced cases of paralysis. So these wheelchairs tend to get more and more expensive depending on how specialized they are. So several of the techniques that are in use include pupil tracking, where the pupil of the eye is tracked by a camera placed very close to the face, and head position control, where the tilt of the head is used to control the motion of the wheelchair. Tongue control, where a marker attached to the tongue is used to control the wheelchair. And at the extreme end, there's also a direct brain interface, where signals are taken directly from the brain of the patient to control the wheelchair's motion. These can be, and usually are, very intrusive, uncomfortable, and highly expensive to use. The idea behind the project. So my idea is to create a new design for patients to interface with wheelchairs which satisfy multiple requirements, that is objectives. So I'm going to list the objectives that I kept in mind while doing this project here. So the first objective is for it to be effortless. So I want the interfacing method to use zero force for interaction, so that even patients who are unable to operate joysticks and keypads should have no problem using this method. It should also be highly customizable, so that the design is applicable to the maximum number of patients possible. It should be inexpensive, so that it is accessible to patients of all economic standing. It should also be simple, so that cost of implementation is kept as low as possible. So for our design, this means that we use only a few steering commands. It should also be modular, so that the design can be used to swap out the control module of a standard base model motorized wheelchair, replacing the joystick and the keypad. So I feel that this is an innovative and application oriented project that could satisfy the requirements for this course. The key idea behind the project is that many paraplegics and quadriplegics can move their fingers and toes to a small extent, even if their limbs are actually paralyzed. A famous example is Dr. Stephen Hawking, the famous theoretical physicist. So till recently he could move two fingers in his hand, which was used to operate his wheelchair, even though his entire body was paralyzed due to advanced motor neuron disease. So in many of the patients, this movement may not be enough to operate existing wheelchairs, but if we were to use an optical method to capture the position and motion of fingers and toes, we could use that to control a wheelchair using image processing techniques, and that is the key idea behind this project. Design. So here is a block diagram view of the design. So it's divided into 3 blocks. The first block takes care of capturing the hand position. The second block takes care of processing the captured images, and the third block reads the signals from the processing block and controls the wheelchair itself. So here is a conceptual render of the design in action. So over here on the right palm rest is the position capture block, so the patient can sit in the wheelchair and his hand would rest on a surface here, and there would be illumination coming up from underneath, and a camera positioned above it would be able to capture a silhouette of his hand and send it to a processing system. The processing system can be an onboard embedded Windows system minus the monitor, which could run MATLAB code that I created for this project. It could be typically located at the back of the wheelchair, and it communicates via serial link towards the motor control microcontroller board. Looking back at the components of each block, so as you can see, the position capture block consists of an illumination source, which could be an LED matrix to provide uniform illumination to the hand from behind, a diffuser which will diffuse the light from the source so that it doesn't create any artifacts, a transparent support on which the user's hand or foot could rest, and a webcam which is capturing the image. Processing and control consists of the MATLAB source files. Template files are the files that are created during an initial training step, where the different commands available to the user from the wheelchair are mapped to different hand positions. There is a GUI for the customization and debug, during which a monitor needs to be connected, but There's no need for a monitor for future operation during the steering. And then serial communication aspects of the code. So in the implementation that will be shown, the serial parts of the code are commented out because there's no hardware that controls the wheelchair as yet. The wheelchair interfacing part consists of a serial microcontroller board, motor drivers and wheelchair motors. The board receives serial signals from the MATLAB code and causes the motor drivers to switch directions or stop the wheelchair motors. As I mentioned earlier, the position capture block is physically fitted into the palm rest of the wheelchair. It could also be fitted on the footrest depending on the needs of the user. The silhouette of the hand is produced using the illumination so that future processing becomes simpler. All this is done to make the design economical. It uses an inexpensive USB webcam for image capture, and the illumination can be done by an LED matrix consisting of really inexpensive LEDs arranged in a grid. The processing and control block consists of the major image processing side of the design. It consists of a Windows processor that is capable of running MATLAB code. So the code supports 5 steering commands. These are forward, reverse, turn left, turn right, and brake. Different hand positions are assigned to these commands, and when they are reproduced by the user while in steering mode, the system will obey this. Each of these commands are captured multiple times during the template creation process to take care of variability during the user's reproduction of the same. The code consists of a GUI which is presented, which can be used for debugging as well as training the system in the beginning, and the system operates on maximizing the correlation to match between different templates so that the correct command is picked after observing the user's hand position. Matching is performed only on every 6th frame so as to save on processing. The response time is still in the order of milliseconds. So the system has a couple of safety features built in, such that whenever there's any unexpected behavior or whenever a hand position cannot be matched to a template, the system will break and not move unexpectedly. This is so as to prevent accidents from happening. So here is a picture of the GUI. As you can see, the hand's silhouette is captured and it is matched against a set of templates, and the interpreted command is displayed here. Commands can also be sent over the serial port, and code for this is included but commented out. Can be sent over the serial port to microcontroller boards which can control hardware from this point on. There are several buttons here which can be used for debugging and tuning. This window over here is AMCAP, which is used for controlling the characteristics of the input webcam. And the wheelchair interfacing block, as mentioned, consists of a USB microcontroller board which runs some firmware and is connected to a motor driver circuit. Depending on the commands being sent by MATLAB, the motor drivers can be switched and the wheels can be spun to obey these commands. For example, to turn left or right, the wheels can be spun in opposing directions. Functionality, so typically the user goes through the setup process so that the system becomes accustomed to his preferences on the first boot. comfortable hand positions should be created so that they can be easily reproduced, and these positions are repeated up to 4 times in this current implementation so as to take care of variability. After this, the system can be put into steering mode, and the monitor that is used during the initial template creation process can be disconnected. The user then recreates these hand positions in front of the image capture to control the wheelchair, and the system ideally responds within milliseconds. All mismatches default, and idle behavior is treated as break to ensure the safety of the user. Conclusion. So the goals presented in the initial proposal have been met. However, the physical implementation of the design is confined to a laptop and its USB camera at the moment. The system is capable of responding smoothly to changing hand positions. However, due to the lack of availability of a microcontroller board, I am not able to demonstrate the hardware switching. However, I have implemented serial port communication, which is commented out in the attached code but can be easily re-enabled. So potential improvements in performance of the algorithm can be achieved by using any of the commercial or academic matching algorithms rather than the brute force correlation matching that is used in this. This works well because of the non-strenuous response time requirements, because users are not expected to change their hand position within a fraction of a second. And from now I'll be giving a demo of the system in action. So this is the demo of the hand position based wheelchair control interface. So you can see the GUI of the system on the screen. You can see several buttons here that perform various tasks. So the create template button is used to create templates so that the different commands can be assigned to different hand positions. So I'll demonstrate that now. So all you have to do is press create template, and then it will ask you to assume the hand position, and then press the button again to capture the first copy of that template. So I'm pressing it, and the camera has acquired my hand, and it asks us to press again and again. So each time you are expected to vary your hand position so that a new gesture can be created. And now I'll skip forward so that I can show you a demo of the steering mode in action. At this stage I have already created the templates, and I have pressed the start button. So the system is now in steering mode. This is the default mode where my hand is not on the illuminated plane, and the system is now in brake so that the wheelchair does not move. I'm going to bring my hand in front of the screen so that my silhouette gets captured. So initially I am bringing it into the forward position, and as you can see, it smoothly captures it. Commands can now be sent over the serial port to any connected microcontroller board, and motors can be tuned. I am now moving my hand to the next position, so it has detected that as turn right, and now I'll move my hand to the other side so that I get the turn left, I'm sorry, and moving it below gives me the reverse position. So I can smoothly switch between positions and the system will detect it. So turn right, forward again, turn left, and finally reverse, and I can come out of this mode by pressing the stop button. And now the template creation button is again accessible, so I can use it to create another template, or I can just set it into steering mode and remove the monitor, and the system will work from this point on. And that concludes the demo. Thanks for watching.